So catalyst is a substance which alters the rate of the reaction without itself undergoing any permanent chemical change. So by the end of the reaction, we'll obtain the catalyst as it is. It just alters the rate of the reaction. A catalyst helps in attaining the equilibrium faster. That is, it catalyzes the forward as well as the backward reaction. So energy barrier, the collisions are effective only when the molecules possess energy greater than or equal to the threshold energy. Hello everyone, this is Ambli Unnikrishnan from the Department of Chemistry. So today I'm back with the last session of the chapter Chemical Kinetics. So in the last session we discussed the temperature dependence of the rate of the reaction and what is Arrhenius equation, what is activation energy, as well as the qualitative increase in reaction rate with temperature. Right. So in today's session we are going to study what is the effect of catalyst. How does the catalyst or addition of a catalyst change the rate of the reaction, as well as what is collision theory of chemical reaction and what are effective collisions. So first let us begin with what is the effect of a catalyst on the rate of the reaction. So what is a catalyst? Catalyst is generally a substance that we are using to increase the rate of the reaction, or else it alters the rate of a reaction, or to speed up the reaction we'll use a catalyst. So the importance of this catalyst is that catalyst will take part in the reaction, it will alter the speed of the reaction or rate of the reaction, but it will not get consumed in the reaction. By the end of the reaction, you will get the catalyst as it is. Right. It will take part in the reaction, but it will not form any products. Its duty is just to alter the rate of the reaction. Right. So catalyst is a substance which alters the rate of the reaction without itself undergoing any permanent chemical change. So by the end of the reaction, we'll obtain the catalyst as it is. It just alters the rate of the reaction. Right. So KClO3 gets converted into KCl and ozone, and here MnO2 is used as a catalyst to increase the rate of the reaction. Right. Now what is intermediate complex theory? Right. According to this theory, a catalyst participates in a chemical reaction by forming temporary bonds with the reactants, resulting in an intermediate complex. This has a transitory existence and decomposes to yield products and a catalyst. So what does this intermediate complex theory says? Catalyst will be there, which we are going to add to this reaction. So the reactants and the catalyst will form an bond, which is a temporary bond, and what it will happen, it will form an intermediate complex. So this intermediate complex will be between the reactants and the catalyst. Then what will happen, intermediate complex, as it is unstable, it will start breaking the bonds, and the bonds between the reactants and the catalyst will break. It will form the products. Right, reactants will form the products, and what will happen, we'll obtain the products as well as the catalyst. So that intermediate complex is formed with the bonds between reactants and catalysts, that is called as the intermediate complex theory. Right. Now, catalyst provides an alternate pathway or reaction mechanism by reducing the activation energy between the reactants and products, hence lowering the potential energy barrier. So, what is exactly the use of catalyst? It will increase the rate of the reaction. So, how does it increase this rate of the reaction? It will reduce the activation energy. So, what was activation energy? That is, if this is your reactants and these are your products, the energy which is required by the reactants to form this activated complex, that is called as activation energy, right? So by the addition of catalyst, before the addition of catalyst, this was the activation energy, this much was the activation energy. Now by the addition of catalyst, what is happening here exactly? The activation energy is reducing, only this much is required. See, from here to here. So you can see, before adding the catalyst, this much activation energy is required. After adding the catalyst, only this much activation energy is required. So when activation energy is less, easily the reactants can undergo collision and form the products. So this is activation energy without the catalyst, and here it is with the catalyst. Right. So that is the importance of the catalyst. It actually increases the rate of the reaction by decreasing the activation energy. I hope it is clear. Right. Now, some characteristics of a catalyst and catalyzed reactions. A small amount of catalyst can catalyze a large amount of reactants. Even there is a large amount of reactants, only a small amount of catalyst is required. A catalyst does not alter free energy change of a reaction, and it does not alter the enthalpy change. So there is no effect on Gibbs free energy or enthalpy of a reaction by the addition of catalyst. A catalyst can catalyzes the spontaneous reaction but cannot catalyze non-spontaneous reaction. So what does that mean is that the duty of a catalyst is just to alter the rate of the reaction. Catalyst cannot initiate a reaction. If the reaction is not a spontaneous reaction or a non-spontaneous reaction, means it requires some external agency to start the reaction. But that duty can't be done by a catalyst, right? That can be done by an external source. But the only duty of a catalyst is to alter the rate of the reaction. It can't initiate a reaction, right? A catalyst helps in attaining the equilibrium faster. That is, it catalyzes the forward as well as the backward reaction, right? It catalyzes the forward as well as backward reaction to same extent so that the equilibrium state remains the same, but it is reached earlier. So this is also an important thing to remember. By the addition of catalyst, equilibrium position will not be changed. That is, the equilibrium will be attained faster, but the equilibrium state will remain as it is, right? That is because catalyst will increase the rate of forward reaction as well as backward reaction to the same extent. So the equilibrium state will remain as it is, but the time with which the equilibrium will be attained will be faster, right? Now moving on to the next important part, that is collision theory of chemical reactions. So till now I was discussing about the collisions taking place in reactants so that it will form the products, right? So that theory is called as collision theory. So let's see. According to this theory, the reactant molecules are assumed to be hard spheres. They are considered as spheres like this, reactants, and a reaction is postulated to occur when these molecules collide with each other. So how reactions are taking place? Reactants are considered as spheres and they will collide with each other and form the products, right? The number of collisions per second per unit volume of the reaction mixture is known as collision frequency. So how many collisions will take part between the reactants per second per unit volume is called as collision frequency, represented by the symbol Z. So for a bimolecular elementary reaction means single step. Bimolecular means only two molecules are present. So A plus B giving products. The molecularity is 2. There are one here and one here, so total 2. So now the rate of the reaction can be represented as rate is equal to ZAB into e to the power E minus EA by RT. So you are already familiar with this equation, Arrhenius equation, K is equal to A into e to the power minus EA by RT. So here rate stands for the K itself, and instead of A we have written ZAB, which is the collision frequency of A and B. I hope it is clear. So where ZAB represents the collision frequency of reactants A and B, and e to the power minus EA by RT represents the fraction of molecules with energies equal to or greater than the activation energy. Comparing with the Arrhenius equation, we can say that A is related to the collision frequency and all collisions do not lead to the formation of products. This is also very important. So by just comparing these two equations, we can say A is ZAB in this particular equation. And what is important to remember, just now I told that reactants will undergo collision and form products, but all collisions will not undergo the formation of products. So only those effective collisions which will lead to the formation of products. All collisions, that is reactants will undergo collisions of course, but all collisions will not form products. Only effective collisions will form products, right? So what is effective collisions then? These are those collisions which lead to the formation of products. The number of effective collisions is governed by the following two factors. So only effective collisions will give you products, and what are the factors in which this collision depends upon? That is effective collisions. One is energy barrier, another one is orientation barrier. So energy barrier, the collisions are effective only when the molecules possess energy greater than or equal to the threshold energy. So threshold energy is a minimum energy which is required by the reactant molecules so that they will form the intermediate, right? That is the activated complex. So that threshold energy, the reactant molecule should either possess that threshold energy or more than that. Then only it can undergo effective collision. So that is one factor, energy barrier. It should consist threshold energy or more than that. Now orientation barrier, the reactant molecules must collide with favorable orientation in order to facilitate the breaking of old bond and the formation of new bond. That is, there is a particular orientation or direction in which these two molecules should collide. Then only the effective collision will take place. So imagine if one molecule is going in this direction and another molecule in this direction, of course they are not going to happen a collision here. This won't be effective collision, right? There is a particular direction in which these two molecules should come so that they will collide effectively. Let's take an example of the formation of methanol from bromoethane depends upon the orientation of the reactant molecules as shown. So you have bromomethane here, CH3Br, reacts with OH minus and it forms CH3OH and Br minus. So what you can see here, this is CH3Br and you have the OH minus here. So here, first one we have taken here is improper orientation. So improper orientation means this OH minus is going to attack the carbon atom from this direction. So is it possible? No, because the bromine is already present here. So what is going to happen? No product will be formed because already the bromine is present in this direction. So can the OH minus also attack from this direction? No. So what is the proper orientation then? The OH minus should attack from this direction. So OH minus will be attacking the carbon atom and forming a product here. At the same time, the carbon-bromine bond is going to break and the bromide ion is going to get released. So what you will get? An intermediate state you will get wherein OH bond and Br bond will be there. And what is going to happen? This bond is going to break, this bond is going to form. So you will get methanol and Br minus will be released. So already as the Br is present in this direction, the OH minus, that is the other reactant molecule, should not come from this direction. It should come from the opposite direction. So that is called as a proper orientation. If it is not a proper orientation, product will not be formed. So these are the two factors which depends: energy barrier and orientation barrier. I hope it is clear, right? Now, the proper orientation of reactant molecules lead to the bond formation, whereas improper orientation makes them simply bounce back and no products are formed, right? So, to account for effective collisions, another factor P called as a probability or steric factor is introduced. Okay, so there are two factors as I told you, that is one is energy barrier and another one is orientation barrier. So both of this we have to accommodate in this particular equation. So the equation becomes rate is equal to P into, that P stands for the orientation, right? That is called as a probability or steric factor. ZAB is the number of effective collisions into e to the power minus EA by RT. So this is the equation which is accommodating both these factors. Thus in collision theory, activation energy and proper orientation of the molecules together determine the criteria for an effective collision and hence the rate of chemical reaction. Okay, so what you have to remember, random any collisions will not give you products. It is the effective collisions that will only give you the products, and the factors on which effective collision depends is, one is activation energy, that is reactant molecules must require a activation energy or more than that. Another one is it should come or collide under proper orientation. I hope it is clear. So by this we come to an end to this chapter chemical kinetics. So I hope the chapter is clear for you. So in the next session let us meet with a new chapter. Thank you.